If you've ever flown in an airplane and noted the outside temperature, which they sometimes display on the screen in front of you, you probably saw that it was really cold, like negative 50 degrees or so. This just reinforces what most people know. As you go up, it gets colder. That's why there's snow on the top of Mauna Loa volcano in Hawaii, as shown in this picture, even though it's in the tropics and there are palm trees growing at sea level. The question I want to address in this video is why? Why does it get colder as you go up, and how can we predict how much it will cool? The quick answer is that cooling is caused by air expanding as it rises. This process is called adiabatic cooling. Adiabatic means that the process is a closed system with respect to energy. No energy in, no energy out. First, some background. As you probably know, the air pressure on Earth is due to the weight of the overlying gases in the atmosphere. Since there are fewer gas molecules above you as you rise, the pressure decreases as you rise. The increase in pressure towards the surface causes the air density to increase too. As a result of the decrease in pressure with elevation, a mass of contained air will expand as it rises. One way to see why this is happening is to imagine containing the air in rubber, like in a balloon. As you release the balloon and it rises, the air inside presses out against less and less pressure, which causes the balloon to expand. Now here's the key part. The expansion of the balloon stretches the rubber, and this requires thermodynamic work. Well, real work too if you've ever tried to blow up a balloon. In thermodynamics, both heat flow and work are expenditures of energy, which should make sense. It takes energy to blow up a balloon, and when the balloon's rubber is stretching as it rises due to expansion, surely work is being done. But we've stipulated that the balloon is a closed system, so no energy can get in or get out. We can't, for example, add heat as the balloon rises to provide the energy needed to stretch the rubber. So where does the energy come from? The answer lies in the thermal motions of the gas molecules in the balloon. As you probably know, the vigor of motion of gas molecules is related to their temperature. The hotter the gas, the more vigorously and rapidly its molecules move. Hot gas molecules have more energy than cool gas molecules. This suggests a way to extract internal energy from the molecules inside the balloon. Simply slow them down. Or, saying it another way, simply cool the gas. The cooler gas has less energy, and the energy difference can be used to do the work on the rubber, stretching it as the balloon expands. The cooling required to provide the energy for expansion is called adiabatic cooling. If we go back to the first figure again, note that the vertical scale and temperatures are calibrated. The gas cools approximately 10 degrees C for every 1,000 meters, or 1 kilometer. This rate of cooling with elevation is known as the dry adiabatic lapse rate and applies when the rising air is dry. Why, you may ask, do we have to stipulate that the rising air is dry? Well, that's because you should recall that energy is released when a high energy gas phase like water vapor transforms into a lower energy liquid phase like water. So if the rising air is simultaneously precipitating water, then heat is continuously being added to the system. Let's think of this in terms of energy. During dry ascent, energy is continuously being removed from the air molecules in order to pay for the needed work of expansion. This extraction of energy comes at the expense of temperature, so the air cools at about 10 degrees C per kilometer. But if the air is continuously precipitating during ascent, then this extraction of energy is partially balanced by an addition of energy from the latent heat of evaporation, the energy given off when water vapor transforms to liquid water. Here we can see our balloon continuing to expand, requiring energy, but we can also see raindrops forming which continuously supply energy. The energy added is still less than the energy extracted, but it offsets the temperature decrease and results in a smaller rate of cooling with ascent. The cooling rate that occurs when the rising air is also precipitating is called the moist adiabatic lapse rate and is only 6 degrees C per kilometer or 0.6 degrees C per 100 meters. The reason the air cools less rapidly is because it is simultaneously being cooled by the expansion and heated by precipitation. One more thing I should also mention. As we've discussed, air masses cool as they rise, but this also means that they warm when they sink, right? So it goes both directions. As air masses are rising, they're cooling and expanding, and as they're sinking, they're compressing and warming.